surprise, we're not talking about differential geometry yet. But the good news is we are going to be talking about how tensors actually transform. So what I'm going to do in this video is I'm going to restrict to the case of vector spaces, right? So modules over a field. So we're going to talk about vector spaces. You can probably just think about real numbers again the whole time. And I'm going to go over some basic linear algebra about transformations of matrices and dual vectors. So hopefully those are familiar concepts to you, but we'll go over some of that. And at the end of this video, we're basically going to derive the transformation law of a tensor, right? The joke is a tensor is something that transforms like a tensor. But how does a tensor transform? Now, we're only going to be talking about this in terms of a tensor as a multilinear map. Technically, in order for the full proper physics definition of tensor, you need to have things like a manifold and a tangent space, and we will get into that in later videos. But if you're not concerned with the technical definition so much, this is the video that tells you how a tensor transforms, and you just need to plop in some dx's in the appropriate spot. So with that being said, of course, if you have any questions, comments, concerns, please just, let me know. It's what the comments are for in the video below. And let's just jump right to it. So we're starting off in this case with some vector space V. And let's suppose that we have two bases. So I'm going to have one basis. So it'll be EI, maybe I goes from 1 up to N. And some other basis of vectors I'm going to label by Fi. And suppose if we have a change of basis, right? So we go, we want to change our basis from this set of vectors E sub I to this basis F sub I. Then we can write this in terms of, so any vector written in the old basis is going to be equal to this change of basis matrix multiplied on the left by the components of the vector written in the new basis. So I'm going to use some maybe not entirely correct. Well, I don't want to say not correct, but I'm going to use some formal notation here. So I'm going to write actually my basis vectors as a row matrix. And so I'll do the same thing with F. So I'm going to use, when I just write E, I mean this row matrix. And when I just write F, I mean this row matrix. But so these are not vectors, right? The entries of this row matrix are vectors themselves. And so this is going to be just a notational convenience for now to keep track of this stuff. So it's important to keep in mind as we're going through this, when are we talking about an actual vector? When is this just a matrix populated by vectors as a notational convenience? So writing out this change of basis formula basically for these vectors is what we find is that for each individual, say F sub I, that is equal to the sum of j equal to 1 up to n of a j upper I lower, and I'm going to explain this in a second, multiplied by ej. Now, the reason why we do this, right? So normally when you have some matrix, some matrix X, we normally write both the indices in the lower component. But now, if you've heard about tensors before, you probably know that there's something with the upper and lower indices. And the reason that we do this is there's this consistent notation / convention called the Einstein summation convention, where instead of writing all these uppercase sigmas, we're going to see towards the end of the video, it's really inconvenient to have to write all of these. So we're just going to write a lower I upper j, E lower j. And so the convention, the Einstein summation convention simply says that if you're looking at any formula and you see an index in the upper part of it, and you see it in the lower somewhere, it could be on the same symbol or on different symbols, but then it is implied that you're summing over all of those possible indices. So that is what the Einstein summation convention is. Okay, so using that, what we're going to do now is we're going to write the components of our vector. So suppose we have some arbitrary vector v, and we're going to write it as components. So it'll be v uppercase I, and then in square brackets, I'm going to write e. So what I mean by this is going to be the ith component of the vector in the basis provided by E. So we can write V using the Einstein summation convention, right? So by definition, this is the coefficient of EI for the vector V in this basis E. So writing this out in our Einstein notation convention, I'm also going to let if I simply write V, so now I'm talking about the total vector, square brackets E, what this is going to be is the column vector. The column vector of V in the basis E, right? So as a matrix, so now this really is a vector. It's populated by scalar entries. As a vector, this is going to be V1E in the first entry, ... down to Vn E. Okay. And so now, all I'm doing is defining a bunch of notation so far, right? And we want to start putting it together to see some new / interesting / useful sort of things. So now what this allows us to do is I can take my vector E and I can actually write it if I take, now here again, we're mixing formal and proper notation. So if I take my this column matrix V at E here, and I multiply it by this row matrix, which this is just a formal matrix containing the basis vectors E, that is going to reproduce this expression up here and gives us our vector E in that basis. So by the exact same argument I did, we can also write E in the basis F. So I could write it as the row matrix F multiplied by the column matrix whose entries are the corresponding coefficients of V in the basis F. So writing things out like this, and then taking this, compactifying this formula above that tells us how to translate between the two bases, we also see that the row matrix F is equal to the row matrix E multiplied by the change of basis matrix A on the right. And this is going to give us a transformation rule, the so-called contravariant transformation rule, which I will explain the notation of in this video. So we have that E multiplied by V of E. This is our vector V, which we also know is F multiplied by V at F. And then if we expand this out, right, well, we know that F can be written as E A V at, again, we can expand out F as E A. So rearranging these terms then, what this means, so since this is going to hold for every possible vector, then it must be the case that V in the basis E is equal to A multiplied by V in the basis E A. In other words, multiplying by inverse matrices, we find that F in the basis, V in the basis F, well, this is V in the basis E A, which is A inverse times V in the basis E. And so this is our transformation law. I'll just highlight it here with one of my favorite rainbow colors. So this is the so-called contravariant transformation law of vectors. So why contravariant? Well, it's because it changes with the inverse, right? So contrary to the change of basis matrix. So if you want to take a vector V, you want to write it in a new basis, which is prescribed by the change of basis matrix A, then this is contravariant because the way to do that is to multiply your column vector on the left by the inverse of the change of basis matrix. So maybe you've heard of the term covariant as well in the context of tensors, contravariant and covariant. And so you can probably guess that the in covariant means that we're going to have some sort of transformation law involving instead just the change of basis matrix. So that's what we're going to get into right now. But first, I just want to remind you, so hopefully you've seen dual spaces before. So this is just going to be a really lightning quick introduction to them. Suppose you have a vector space V, then alpha, a functional on your vector space. So I'll just talk about real vector spaces for now. So a functional on your vector space, this is just a function that eats vectors V and spits out real numbers R. And this is, and we want alpha to be linear. So that means that alpha, you know, A, U plus V, U and V are vectors, A is a scalar. This should be A times alpha U plus alpha V, right? It's a vector space. The interesting structure of vector spaces is the linearity, the fact that we can take linear combinations. So of course, the maps that we're interested in are ones that respect linear combinations. So supposing that we have such a thing, it turns out that this gives us a vector space. So we sometimes call it V star. We call it the dual space, which in fact is isomorphic to the original vector space when this is finite dimensional. So V star is the collection of all such linear maps. And of course, I should tell you what the addition and scalar multiplication is. Suppose you have two linear maps, alpha plus beta. Well, how does that act on a vector U? What's our addition operation? Well, it's just sort of the obvious thing, right? You apply alpha to U and you apply beta to U and you add those end results together. Same thing. So what, you know, for scalar multiplication, what would A alpha on the vector U be? Well, of course, you just apply alpha to the vector U and scalar multiply by A. And it turns out that if we have a basis of our vector space E, so, we have a basis E, right? These E sub i's of our vector space V. It turns out that there's a natural sort of choice of basis induced from this E lowercase, and we often write this as E uppercase. And we define this as the function. So it's enough to simply prescribe how this function works by the linearity properties. It's enough to prescribe how it acts simply on the basis vectors, and then extending by linearity, you can see how it works on every single other vector. And so we can define E sub I by acting on these E sub j's. So these are functions on our vector space. This is our basis of the original vector space V. And we're going to say that this is equal to 1 if I is equal to j and 0 otherwise. Okay, so hopefully this is enough of an introduction, but I'm counting on the fact that maybe you've seen this before. Again, if you have questions, comments, concerns, feel free to just leave them below. So now that we have this, I want to take an arbitrary functional and I want to expand this out in terms of my basis E upper I. And in terms of this basis, depending on my original basis, E lower I. Now, if I just write these components as the alpha lower I for a moment, so again, this is Einstein summation convention. It's implied we have this sum. Well, what does this look like? What does alpha look like acting on some arbitrary vector on my space, right? So I'm just going to write this as the sum of C upper I. So these are scalars, E lower I. Well, what's going to happen is this whole sum of alpha lower j's times E upper j's acting on C upper I, E lower I. And notice that this is only, so I guess by linearity, I can rewrite this. I can pull my CI out in front, and this is going to be alpha sub J, E upper J on EI. And notice that this is only going to be non-zero when I is equal to J. So in other words, this is only going to be non-zero when we have I is equal to J. So that means CJ, alpha J, EJ, and E sub J here, which is just CJ, alpha J down here, because this is equal to 1 whenever these indices are equal. So in other words, if we think about this as being, so we want to determine, what these coefficients are. So imagine instead of having this sum, right, if we just had alpha acting on a single one of these basis vectors, then we see that that gives us precisely alpha sub I. So alpha at EI is alpha sub I, because in this case, each of these C coefficients is equal to 1. And there's only one case when it's non-zero, if we're taking this to just be the single vector EI. So I realize that might be a little bit confusing if you're not used to this sort of tensor notation. So if I lost you there for a second, don't worry about it. That's just a little bit of motivation for us to define. So we're going to write alpha sub I square bracket E to be, by this we mean alpha applied at E sub I, which is precisely by this argument that is that coefficient alpha sub I that we're looking for. But we use this specific notation to say alpha sub I in the basis E. Well, in fact, there's a little bit of confusion here, right? So the important part is, to remember is that we're actually starting with a basis of the vector space E. And now for our vector space, the dual space V star, we're talking about this basis of E upper I's induced by the original basis. And so we're going to see that the bases on both sides sort of work together, because you could go in the reverse direction if you had a basis of V star that would give you a basis of V. So the point is, though, this is the notation that we're going to use for the coordinates of this functional. And then in that case, what we have is alpha sub I in the basis F, right? This is alpha acting on the basis vector F sub I. Well, what is this? Going back to our equation above for the change of basis matrix, this is going to be A, the change of basis matrix, superscript J, lowercase I, E, J. But alpha, remember, we're assuming is a linear functional. So that means that, namely, alpha distributes through the sum. And we have a sum because you can see that we have an upper J and a lower J by the Einstein summation convention. So this is really alpha, lower I, upper J, A, lower I, upper J, multiplied by alpha, evaluated at EJ. So in other words, we find that alpha I in the basis E, in the basis F, this is alpha I superscript J, alpha. Now, remembering by this definition, this notation that we're using, alpha sub J in the basis E. So therefore, using this sort of formal kind of notation again, what I'm going to do is I'm going to write alpha sub E. This is going to be the column vector, alpha I, well, in fact, in this case, we have a bona fide column vector because it's actually populated by coefficients. So it's going to be those coefficients of alpha in the basis E, the basis induced by E. And then the above expression, well, we know that this equation holds. So in other words, rewriting this side of the equation, that now tells us that we have here alpha E, well, combining the equation on each one of these entries together, it tells us that alpha represented in the basis F is equal to the vector of alpha represented in the basis E multiplied by the matrix A on the right here. So in other words, we have alpha, if we take our basis E and we transform it by some matrix A, we now have the overall effect of multiplying by A on the right. So let's go up and compare. So in this case, so if you remember back down here, or up here, I should say, we found that for a regular old vector, it satisfies the contravariant transformation law, where we multiply by A on the left. Well, in fact, we multiply by A inverse on the left, hence contravariant. Meanwhile, for functionals, if we wanted to perform the change of basis, A actually shows up now here on the right side of the equation, and it's no longer A inverse, it really just is A, so it transforms with the change of basis matrix, which is why we call it covariant. And now you might wonder, okay, there's this, on one hand, we've got, bona fide vectors on the left, the other hand, we have bona fide vectors on the right. Part of this is reflected in the fact that you might have seen the dot product of two vectors, reaching back to some linear algebra. This can be represented as, if we think about our vectors in terms of columns and rows, and we normally think about our vectors typically being column matrices. So it turns out the corresponding dual vector can be represented simply by the transpose as a row vector. And the multiplication here gives you the good old dot product of vectors. So just a little side note about that. Okay, so we've talked about covariant and contravariant vectors, and finally now we get to put this together in terms of a multilinear map. So at the end of the last video, I told you about the basic definition of a multilinear map. And so we want to know, how does a multilinear map change under a change of basis? Remember that if you have, just suppose uppercase X is just a linear transformation of a vector space V, right? And suppose we have our change of basis matrix A, then you may or may not recall from linear algebra that in order to figure out, well, what is X in the new coordinate system, you simply conjugate by the change of basis. And this tells you how to write the matrix for the linear operator in the new basis. So we're going to combine these ideas to the general notion of a multilinear map, which for us now, we're going to restrict, again, to the case of vector spaces. So suppose, we want to know the transformation law where we have a tensor product of V with itself some number of times. And then we want to take the tensor product of V star with itself some number of times and toss this in. And remember, we don't have to put the braces anywhere because it's associative. And so we can just think about this as some sort of continued tensor product of vectors. So it's going to be a linear map, right? Say into the real numbers. Again, secretly, this all works, for any field. And in fact, modules over a principal ideal domain is basically where linear algebra really happens. And so what does this transformation law look like? Well, let's just slow down first and let's separately figure out if I have a linear transformation on my vector space and a linear transformation on my dual space. So we're gonna, T will be this one first. but we're going to work through both of these cases using the notation of covariant and contravariant up above. We're going to see how to write out T in these individual cases, and then finally put them together to get the full transformation law. So in order to see how that happens, I'm now going to, just to try and keep the notation tidier, I'm going to write T hat to mean T in the new basis. So we already know that T in the new basis is A inverse multiplied by our matrix T multiplied by A. And I'm going to write this out in terms of our Einstein summation convention. This is T hat K L. So remember that we're now writing our matrices with one upper component and one lower component. And this is going to be A inverse. Up here, I'm going to put K I T I J A I L, or sorry, this should be A J L. Okay, so there's a lot going on here. I know this is in some sense hard to look at, but it'd be worse if we had the sigmas here, right? So if we have these two i's, one in the upper, one in the lower, this implies a summation, right? We have one summation from I equals 1 up to n over all these entries. And then we have an upper j here and a lower j here. So there's actually two summations taking place. Okay, and why is this? Why is this the correct way? Well, if you go back, for instance, if you think about just matrix multiplication, say we have some matrices M, M inverse, N, M, right? And you wanted to write out the K-elf entry just in your normal linear algebra definition. If you go through the proper definition with the sums and everything, this is basically what you end up with, right? But I'm just rewriting this in terms of our new, more compact Einstein summation convention, where we don't have to worry about these sums. And now we have our, our indices are in different places. But really, this looks maybe a little fancy and complicated. It's really just a rephrasing of this classical of just matrix multiplication. So now let's unpack what our change of basis means in this case. So we have T, we want to know what is T acting on a vector V. So T will act on V in the old basis first, and then I'll put a hat over all of this to indicate that I'm then changing the basis to see what happens. Well, this should be the same thing. The kth component of this should be the same thing as T in the new basis, whatever that is, we're trying to figure that out, acting on V in the new basis, right? So that is just, we're just applying the appropriate matrix multiplication here. Again, we're just rewriting matrix multiplication in Einstein summation notation. Summation notation, say that 5 times fast, really fun word. So then by this transformation property I just wrote down, we have A inverse, lowercase, let me check my notes here. There's so many indices. I wanted to make sure I got them right. I, J, A, J, L. And then remembering what our contravariant transformation law was for writing V in the new system. So here we're going to have A inverse J on the upper parts. Actually, let me just double check here. So it should be J on the lower part, L up here, and VJ on the upper part of it. But then we know that matrix multiplication, right? All this is a whole bunch of matrix multiplication, with some tricky indices, but we know that that is associative, right? So we can reorder the brackets. And what you see here, if you line up these L's, right? L in an upper, L in a lower, J in an upper, J in a lower, this is just A multiplied by A inverse, right? So by definition, this is the identity matrix. So that simplifies our expression. And what we're left with is A inverse K I T I J V J. But what is this? This is just A inverse ki of, so we have, again, a lower j and upper j here. This is just the matrix multiplication of the operator t acting on the vector v in the original basis. And because we have this I here, that means we're taking the ith component of it. So what that means is this is our, putting these pieces of the puzzle together, this is our transformation law for our multilinear map on the tensors for a contravariant vector, right? For just an ordinary vector of the vector space. And then in the exact same way, again, just recalling some of our linear algebra, what one finds is that if you have some operator, say, let's call it S. So S is now a, this is a linear operator on our dual space, right? So just like we have linear maps from our vector space to our vector space, and we want to rewrite it in a new basis, now S is going to be a linear transformation from the dual space to the dual space. And to figure out how that transforms, so again, just a brief review from linear algebra. So S in the new basis, if we just think about good old matrix multiplication, we end up having conjugation going in the other direction. So here it would be A, S, and now A inverse is on the right. And again, you can just work this out from the fact that we have these functionals. And if you think about that, we have this covariant and contravariant transformation law. Basically, A took on a different role, right? In one case, it was on one side and the inverse. In the other case, it was not the inverse and on the other side. And so putting this together by an entirely similar argument, one would find that the transformation of S acting on an alpha and then transforming to the new basis and asking for the kth component of that, this would be the result of having a ki being multiplied by t applied to alpha in the original basis. And then here we're summing up over the indices I. And so this is what our covariant transformation law now looks like on linear maps. So putting this all together, right? So we have this one transformation law up here and this other transformation law down here. And so now we see for each component of our tensor, right? We want this general case where we now have a tensor with some copy of V, some number of times, some tensor product of V some number of times, and some tensor product of V dual some number of times. So putting this all together, we simply have to apply this original, the contravariant transformation law in each one of these components of our tensor product. And we simply have to apply this covariant transformation law in each one of our components of this multilinear map. And so unpacking everything, I'm going to show you, this is exactly why we need Einstein's summation convention, because the sigmas would be absolutely horrendous. So unpacking all of this, what we find is that for a multilinear map, T, to be written in a new basis, to have its components, we would have, so this would be I1 prime dot 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 up to IP prime. So here, I'm assuming that we have P tensor products of V, and we have Q tensor products of V dual. So down in our lower indices, I'm going to have J1 prime dot 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 all the way up to JQ prime. The transformation law becomes A inverse multiplied by I prime 1, I1 dot dot dot. And we have to repeat this again for each one of these copies of V. We have to apply this transformation law. So we have dot dot dot, repeating this all the way up to I P prime, I P, And then our original tensor with all of the indices in the original basis. And I'm actually going to run out of room. I suppose I'll have to scroll the screen over to the right a bit. So we have our original transformation. So that takes care of the transformation laws for each of the contravariant components. And then we need to put in our matrix multiplication for each of the covariant components. And hopefully you see by now, this is exactly why we have Einstein summation convention. And in practice, things generally don't look as messy like this. We make other notational shortcuts. But finally, here we go. This is the rule. If you have a tensor with some number of components, right, it tells you how to perform this linear map. Each one of these upper components tells you exactly how the tensor behaves on each one of these copies of the vector space V. And each one of these lower components tells you how the tensor behaves on each copy of the dual spaces. This is the full transformation law for a tensor. So you're basically ready to just plug in some dx's from this formula and recover what you've been told in physics class about how to transform a tensor. But next time we finally will get to some differential geometry and talk about the proper way to define things and what a tensor really is.